Hello everyone, welcome to my educational channel. In this lesson we study two tools together, scaling and affinity. You will learn how these tools work and how they are used in the industry. Stay with me and enjoy the lesson.
I got this magic in my fingertips, designing dreams with every click. Shapes and wonders coming to life. With CATIA I cut through strife. In my mind the future's clear. No more doubts, no more fear. Crafting visions in 3D. CATIA's the key, don't you see? I can reach the sky so high. Build my dreams, no need to try. With every tool I sculpt my fate. CATIA helps me innovate. Every line precise and true. Colors bright and brand new. Transforming steel into art. CATIA.
Hello everyone. Today we are going to learn two more tools called scaling and affinity. The first tool is called scaling. Suppose we have a sphere and its center is at the origin of the coordinate system. The diameter of the sphere is 100 millimeters. I activate the scaling command. The settings window of this tool opens. This tool has a very simple settings window. It includes a reference and a ratio. The first option is reference. In the box in front of it, we need to select a reference point. The second option is called ratio. In the box in front of this option, we enter the scaling ratio. This means that if I enter 2, the sphere diameter becomes 200 millimeters. If I enter 0.5, the sphere diameter becomes half of its original size. Values greater than 1 make the part larger, and values smaller than 1 make it smaller. There is one important point that you should know about this tool. With this tool, the part is scaled equally in all directions. At the same time, the distance of every point from the reference changes by the same ratio. Now the reference box is active and highlighted in blue. I click on the point at the origin of the coordinate system. The point does not need to exist before. Notice that I could also right-click inside the box and create a point here. Now I click inside the ratio box. I enter the value 2. Without clicking OK, I click outside the settings window. The preview of the scaled part is displayed. If you look at the part, you can see that it has become twice as large in every direction. I click OK. Now I click the plus sign next to part body in the specification tree. Its contents are expanded. I double click the sketch. The sketch of the sphere opens. Its diameter is still 100 millimeters. Notice that the scaling tool creates a new feature and does not change the original sketch. You can also see a scaling 1 in the specification tree. If I double click scaling 1, the settings window of the scaling tool for the sphere opens. I change the ratio value to 0.5. I click outside the settings window. I click OK. You can see that the sphere has become half of its original size. I double click the sketch. You can see that the sketch size has not changed, so the scaling operation does not change the dimensions of the sketch. Now consider the same sphere with a diameter of 100 millimeters. Its center is now 100 millimeters away from both the X and Y axes. I find the center of this sphere by using the Measure Inertia tool. I also create a point at the origin of the coordinate system. I activate the tool again. In the reference section, I click the point at the origin of the coordinate system. I set the ratio value to 2. I click once outside the settings window. The scaled sphere appears in white beside the original sphere. I click OK. I change the view to the top view. Again, I use the Measure Inertia tool to create a point at the center of the sphere. According to the Pythagorean theorem, the distance from the first point to the origin is about 141.4 millimeters. I measure it. The value is correct. Now the distance from the second point to the origin should be twice 141.4 millimeters. I measure it as well. You can see that the value is correct and is 282.8 millimeters. This means that not only the dimensions of the part but also its distance from the reference point is affected by the ratio value. Now consider a cube with dimensions of 100 millimeters in all three directions. The bottom face of the cube is on the XY plane. I activate the scaling tool. In the reference section, instead of selecting a point, I click one of its faces. I click the top face. In the ratio box, I enter 2. I click outside the settings window. You can see that because the reference is a face, the size increases only in the direction normal to that face, while the other two dimensions remain unchanged. I click OK. I check this result from the side view of the part. Now let's look at the second tool, Affinity. If I want to explain the difference between these tools in one sentence, scaling changes the dimensions of the part, but affinity changes the coordinates of the points. In the previous tool, we changed the dimensions of the part by using the ratio value. In this tool, the coordinates of the points are changed based on a local coordinate system and specified ratios. So, Affinity works with the coordinates of the points, not with the dimensions of the part. With this tool, we can change the coordinates independently along each axis. The process works like this. First, the coordinates of each point are considered separately. Then these coordinates are multiplied by a transformation matrix to calculate the new coordinates of the point. The new part is created from these new coordinates. Now, what is the advantage of this method? Consider an industrial part. It is made by casting. Its dimensions are different in different directions. It is natural that after casting, the part shrinks as it cools down. But because the part is not symmetrical, the amount of shrinkage is not equal in different directions. This tool helps us after the design is finished and when we are preparing the manufacturing drawings. We can correctly adjust the amount of compensation in different directions. Suppose we have a rectangular block with a cross-section of 50 plus 50 mm and a length of 100 mm. The bottom face of this block is on the XY plane. One corner of the block is 50 mm away from both the X and Y axis. I activate the tool. Its settings window opens. This window has two sections. The first section is called Axis System. Here we define the local coordinate system. This section has three options. These options are origin, XY plane, and X axis. First, notice that we can fill in all three options together, or we can define them one by one. In the origin section, we need to select a point. This point can be a corner of the existing model or a point that was created before. In the XY plane section, we select a flat face or a plane. This face or plane is considered the XY plane by the software. The software automatically defines the Z-axis perpendicular to this plane. The third option is called X-axis. After selecting the XY plane, the software first determines the normal direction of the plane. Then it creates a right-handed coordinate system. Now with the third option, we can tell the software which direction should be used as the X-axis. There is a selection box in front of each option. To activate an option, its box must be turned blue. For now, I will not enter any information for these options. You can see that while tool is active, a red coordinate system is displayed. This is a local coordinate system. The tool uses this coordinate system to calculate the coordinates of the points. At the moment, because no information has been entered in the first section, this coordinate system is displayed at the origin. The direction of its axis is exactly the same as the global coordinate system of the software. The second section of the settings window is called Ratio. This section has three options. These options are the X, Y, and Z axis. There is an input box in front of each option. We enter increase or decrease ratio for each axis in these boxes. Now I enter 2 in the box for the x-axis. Without clicking OK, I click outside the settings window. The preview of the final shape appears in white. I measure the distance from the corner of the block to one of the main planes. You can see that it has changed to 100 millimeters. I also measure the length of the block from edge to edge. You can see that it has become 200 millimeters. I click cancel. Now I set the Y value to 2. I click outside the settings window. The preview of the new shape appears. I measured both the corner position and the edge-to-edge length. You can see that the corner is now 50 millimeters farther from the origin. The edge of the block has also moved 50 millimeters and its length is now 100 millimeters. I go back. I activate the tool again. Now I click the box in front of origin until it turns blue. I select the corner of the block. You can see that the red coordinate system is now placed on this corner. At the moment, the direction of its axis is the same as the global coordinate system. Now, without changing the other options, I enter 2 in the X ratio box. I click outside the settings window. The preview of the final shape appears. You can see that the corner of the block stays fixed and does not move. The size of the block is doubled along the x-axis. The coordinates of the points remain unchanged along the other axis. Notice that the final shape must be created in such a way that the new coordinates of all points are correct. I will explain this in the next example. I click cancel. I activate the tool again. I use the corner of the block as the origin of the local coordinate system. The X and Y axes are on one face of the block, matching the global coordinate system. Now I activate the second option in the first section. I click another side face of the block. This face is parallel to the ZX plane. You can see that the red local coordinate system rotates so that its X and Y axes lie on this face. Here the software sets their positive directions the same as the positive directions of the global axis. However, the positive directions of the local axis are not always the same as the global coordinate system. I click the XY plane box until it turns blue. I click the side face of the block. The axis rotates so that the X and Y axes lie on this face. Now you can see that the directions of the axes are equal to the global coordinate system. If I select the opposite side face as the XY plane, the directions of the axes become the opposite as the global coordinate system. I go back and activate the tool again. I use the corner of the block as the origin. The red coordinate system is placed on this corner. In the XY plane box, I select the side face of the block. Now the X and Y axes are located along the edges of the side face. The Z-axis is along the length of the block. I click the X-axis box. I select the long edge of the block. The selected edge is shown as the X-axis in red. Now I enter 2 in the X ratio box. I click outside the settings window. You can see that the length increases in the original direction. Now I place the X-axis on the correct edge. I click outside the settings window. You can see that the length now increases in the correct direction. So if the X or Y axis is selected incorrectly after choosing the XY plane, the length will increase along the previous direction. Now consider a rectangular block. A diagonal line is drawn on its top face at an angle of 45 degrees to its long edge. I activate the tool. I use the corner of the block as the origin of the coordinate system. I change the view to the top view. I select the top face of the block as the XY plane. Now the X-axis option is active. I select the diagonal line as the X-axis. You can see that the local coordinate system rotates. It rotates so that the X-axis becomes parallel to the diagonal line. I enter 2 in the X ratio box. I click outside the settings window. You can see that the shape expands into a diamond shape. Why does this happen? I have created a point at the middle of the long edge of the block. From this point, I have drawn a line perpendicular to the diagonal line. I run the command again. I use the same settings. Now I create a midpoint on the edge of the new shape. From this point, I draw a line perpendicular to the diagonal line. I enter the sketch workbench. I create 2 points at the intersection of the lines. I return to the part design workbench. Now I measure the distance from the midpoint of the original shape to the intersection point. I do the same measurement for the midpoint of the final shape. You can see that the two distances are the same. Because only the coordinates of the points along the x-axis have changed, the final shape becomes a diamond in order to keep the y-coordinates unchanged. Now you are familiar with the Affinity tool and its main applications. In practice, this tool is useful for compensating the dimensional changes of cast or molded arts. For complex parts, finding the best result usually requires some trial and error. That is the end of today's lesson. I hope you enjoyed this lesson. Goodbye and see you in the next lesson.
Let's build the future. Come with me.